And this chapter is entitled Mechanical Properties of Materials. A very important chapter. It gives you a general understanding of how materials behave, how do you select materials, what should be the properties you should be looking for. So we're going to talk about in this chapter. Let's start with something which is interesting. And actually, I'd like to just start by explaining you something on the board. And what I'm saying is that suppose we have talked about this in chapter 1 and chapter 2, that suppose I have a member and I apply a load on this. And this load, let's call it P, and the cross-sectional area is A. Then we said that this is going to cause a stress in the member. And that stress is one of the normal stresses. For example, the stress is defined as P over A. But this is not all the action that takes place because of this load. What also happens is that this member, whose length was this originally, due to the application of that load, let's say it has an extension also. So this is what we call delta L, and original length being L. We defined a strain, and we said that the strain is defined as delta L over L. These are the two important properties we talked about in chapter 1 and chapter 2, stress and strain. Now, what I'm saying here is that, look, when I apply a stress, I end up with a certain strain. What happens if I increase the load? If I increase the load, stress increases because load is in the numerator. And what happens to strain? Strain also increases. More elongation there. Similarly, if I reduce the load, what will happen to strain? The strain will also be reduced. So what the result I am drawing from this is that stress and strain are related to each other. So if you increase stress, strain increases. If you decrease stress, so what is that relationship? That's what we want to find out. And this has been done by conducting a lot of experiments on different kind of materials. And for a ductile material, the stress-strain relationship looks like this. Let me show you a rough, first of all, a rough picture of the stress-strain relationship. So if I were to take stress on this, on the vertical axis and strain on the horizontal axis, I'm saying that this relationship looks something like this. That's the kind of curve you get. A very interesting curve, and we're going to analyze this curve a little in a minute. Let me just follow my PowerPoint slide. What is the next thing I have? So yeah, how do we do this is using what we call a universal testing machine, which is in front of you now. So in the universal testing machine, what you have is basically you got two heads there, this one and this one, and in between you put your specimen. And specimen is constructed or made in a specified manner. I think I have a picture of the specimen also. This is what the specimen looks like. It has an initial diameter of 0.5 inches, and then a 2-inch length is marked there. And then these things are screwed into the heads. And once you have the specimen in position and you know that your initial length is marked, initial diameter is known. Now by making use of this hydraulic head, you start applying you can apply a tensile or a compressive load. So for tensile load, this end is fixed and this end starts to move up. So you're applying a load P on this specimen. As the load increases, as you apply the load, you will note that there's a strain, and this is the load dial, you can read there. And similarly, the computer will be telling you directly what is the stress and what is the strain. So you can directly read stress and strain for an applied load. This is how you find the stress and strain relationship. And as I said, that relationship looks something like this. Let me admit a few people who were there. All right. So, like I said, if you note the readings of stress versus strain and then plot them, it turns out to be a plot like this. A very important graph. I want all of you to be able to draw this. This is for any ductile material. A general graph I'm showing you for any ductile material like steel. And there are a few things which we need to see, which we need to note in this. First is that when there is, of course, there is no stress, there is no strain. So 0, 0 is the first point you can see there. Then secondly, you notice that it goes as a straight line up to a certain point, beyond which then it starts to curve. So this point up to where you notice that stress and strain are directly proportional to each other. This point is called proportional limit, and this value of stress is called sigma PL. PL stands for proportional limit. So let me write this here, proportional limit. Is that. Then there are a few other points for which I need to have a better graph. This is, so this shows you the proportional limit. I can also show you the yield strength here, but it's better to look at the graph which is given in the book and which I am now bringing on my screen there. Please have a look at this graph. So this is the stress strain diagram for mild steel. And once again, you see that this is of this kind that I just drew, something like this. And the important points on this, well, the first thing is you see two graphs there. One is a darker blue, which is the upper one, and then there's a lighter blue, which is this one. What are these two? Well, this is the same graph as this, except that in this case, the horizontal scale is much expanded so that we can see the relationship, this one. So this portion of the graph is really expanded to this. And now you can see that we have a straight line relationship up to a certain point. This point is called the proportional limit, sigma PL. This value of stress here is called the sigma proportional limit. And this point is called a proportional limit. Then the next point you see beyond that, after the proportional limit, you see that the curve starts, the relationship is no more a straight line relationship, it starts to curve. You can see that after this point, it starts to curve. And then what happens? That you reach a point where although you are not increasing the stress anymore, but the strain keeps increasing. You see what's happening? You're not increasing the stress at all, but the strain keeps increasing. And this portion is is somewhere there. Without any increase in stress, the strain, this is called the yield strength. Sigma yield, this one. And sigma yield is a point where after proportional limit, you reach a point where without increasing the stress, the material just yields, it keeps stretching. That point is called yield strength. And obviously, this is something we want to avoid. We never want to reach the yield strength because you don't want extensive strain in your material. So,
was the yield strength the subscript U or the subscript L?
yield strength is subscript Y, this one.
And then what's the additional subscript U and L? What is their difference?
So they're the upper and the lower limits, you know, because yield strength starts from right here and could go up to there, and then it settles down at this point. So this is really called the lower yield strength, and this is called the upper yield strength. All right. So there's the yield strength. Now, first thing I need you to understand is the difference between these two scales. So these two graphs, and the difference is really only in the horizontal scale. The upper one, which is the black scale, refers to the upper graph, which is this one. So in that, you can see that the difference is, so this is, for example, 10%, 20%, 30% strain. But in the blue graph, which is this one, you expand this, so the horizontal scale is now, for example, 0.1%, 0.2%, 0.3%. So there is a difference of about 100 times in these two scales. And so that's how you can now observe the behavior more accurately, because here you see you cannot really find out what is the what's the slope of this line. It's so difficult. So when you expand it to the blue scale, then this graph becomes something like this. It is only showing you this portion from here until here. This is what you see there. It is so much expanded now that instead of finishing here, it is now finishing there. Everybody get the point? So first thing you must understand is what is the difference between these two scales, these two graphs. The difference is the horizontal scale. The upper graph pertains to the black scale and the lower graph pertains to the blue scale. Now, between these, then you can easily point out where will be the proportional limit right there. Because up until there, it's almost a straight line relationship. Beyond that, starts to curve. So this is called the proportional limit. And this stress at this point is called sigma PL, sigma proportional limit. Then after this comes yielding, and yielding, there are two values. There is an upper limit, a lower limit. And sigma Y is basically defined as, so there's a convention here, and the convention is that you go to 0.2% yield strength, which is this, and you draw a line parallel to this proportional limit line. So you draw a line parallel to this, you come somewhere here, this becomes the yield strength of the member. So to find the yield strength, you plot the graph, and then you take the 0.2% point, and from there you draw a line parallel to the original straight line, and wherever it hits, that's a yield strength. Because, you know, it is very difficult to define where will you take yield strength, this point, this point, this point, or this point. So the convention reached is that you go to 0.2% and draw a line parallel to this, and wherever it hits, that's the yield strength. So we will take this as the yield strength for this graph, for example. 36 will be the yield strength, 36 KSI. 36 KSI is the yield strength of the member whose graph you see here. Everybody good? So I would say that you really draw a line parallel like this to the original straight line, and wherever it cuts, that's the point of yield strength. That's the yield strength you read off. In this case, because is not varying, it's the same here as well as there, but the definition is 0.02 or 0.2%. That's where you draw the line. So this is an important thing. How do you define yield strength? You define it by taking 0.2% and drawing a line parallel to the original line, and wherever it cuts the graph, that's the yield strength. Then beyond yield strength, there are a few more points of interest. For example, we have defined already 2 points: the proportional limit, the yield strength, and then the next one you see is sigma u, which is the upper limit or the ultimate strength. This is called the ultimate strength, sigma u. And this, if you read off the graph from here, it comes out to 60, and this is 63 approximately. So the ultimate strength for this member or this material whose graph you are seeing is 63 KSI. So both the graphs are important. This one has not gone into the ultimate strength, but this one has. So this is, you need both the graphs really. This one to find yield strength, this one to find the other important points. Proportional limit, then yield strength, then ultimate strength, and finally this is called the fracture strength, which is sigma F. Right there. All right, everybody good? I expect you to be able to, if I ask you to draw me in the exam, draw me a general stress strain diagram for a ductile material. This is what I want you to show me. Something like what I have drawn on the board also, and something what you see there. So these are the important things you will be showing on that diagram. First of all, to scale, this is the vertical scale is normal stress, and the horizontal axis is strain, and the units of stress and strain, you can see this is in KSI, and this one is in inch per inch like we talked about. And then on this stress strain diagram, you got to show the proportional limit, the yield strength, the ultimate strength, and the fracture strength. Now I have a question. And the question is that I'm saying that the ultimate strength is 63 KSI. That's the maximum stress that it can take. But I'm also saying that fracture strength is 47 KSI, which means it will break at 47 KSI. So how is then the ultimate strength 63? I'm leaving you with this question. I'd like you to think about it, and we can proceed on. So in a stress strain diagram, these are the things I need to show you. There are, I think, 8 or 9 things. Vertical scale, which we said would be sigma. Horizontal scale, which would be epsilon or strain. Then I need you to show me the linear portion and the Young's modulus. What is the Young's modulus? Well, when we talk about the linear portion of this graph, what we are saying is that this linear portion, the slope of this linear portion is given by sigma divided by the strain epsilon. And this quantity is called E for modulus of elasticity. Modulus of elasticity. and E is defined as sigma over epsilon. So if when you are in the linear portion, what it means is that the ratio with which you increase your epsilon and what you will be resulting in terms of the stress which you give will result in a certain strain, and that stress to strain is a constant number which we call E, modulus of elasticity. It is also called the Young's modulus. Young's modulus, after the name of the scientist Thomas Young, who first worked on this. So it is either called Young's modulus or modulus of elasticity, E. This is an important thing. This is the ratio of sigma over epsilon. Please remember this definition. E is equal to sigma over epsilon. And this is, so what will be the units of E? You can see sigma, units of sigma are what? They are, for example, in SI units, they are pascals. So, and Pascal being a small unit, they could be megapascal or gigapascal. And what are the units of epsilon? They would be millimeters per millimeter, in other words, unitless. So the units of E are also megapascal or gigapascal or Pascal even. Kilopascal, megapascal, gigapascal, depending on how many pascals you have. So usually it is not mentioned in pascals, but either in kilo, mega, or gigapascals. This gives you an idea about the strength of the material. So this modulus of elasticity is a good thing to know, and this for every material this is given. It is found in the tables given in your book. How do we define E? E is the ratio. So this is E, this is sigma, and this is epsilon. This is the ratio of sigma and epsilon. It's called the Young's modulus or modulus of elasticity. Everybody good? Then I have yield stress. So yield stress is, like I told you, it's the 0.2% offset. So you take wherever you get 0.2%, you take that. If this is 0.2%, you draw a line parallel to this original line, and wherever it cuts, that's the yield strength. It should usually be a little above the proportional limit. My diagram is not that accurate, but I showed you the diagram there. This is the 0.2% offset. This I need you to show you when you are drawing the stress strain diagram. Then I have the ultimate strength, which is this value, ultimate stress. And you read it off here, sigma ultimate. And then I have the fracture stress, failure stress or fracture stress, which is somewhere there, which you can read off the graph also. And that's a question I'm leaving you with. Why is the failure stress less than the ultimate stress? If I can go to the ultimate value, which is higher, then how come I'm saying that the failure occurs at the lower stress? This is a question I'm leaving you with, and I would like you to answer me this question tomorrow. All right, now I'm going to show you the table of values for every material. This kind of experimentation has been done. For stress and strain diagrams have been drawn, and the values have been plotted. Here is the one of the tables given in the back of your book. Average mechanical properties of typical engineering materials. So the first column lists the materials, the kind of engineering materials you see are aluminum alloys, cast iron, copper alloys, steel alloys, titanium alloys, even concrete, plastic, wood, and some selected structural grades, which are also given. So these are all the different type of engineering materials used, and then you have the mechanical properties listed on the right hand side. For example, the first one is specific weight. And then you have the modulus of elasticity E. We just talked about this. And then also there's some more modulus of rigidity. We are going to talk about it maybe tomorrow. Yield strength is sigma y, we talked about it. Ultimate strength, we talked about it. Elongation, Poisson's ratio, we'll talk about it tomorrow. Now, the thing to note is that there are two graphs in the back of the book. The first one is in US customary units, and maybe I have the other one also, which is in basically the SI units. So the important thing what I'm trying to say is that you should consult the chart. So there are two tables. One of them is in the English units or US customary units, and the other one is SI units. First of all, you should see which type of units are you dealing with in your question. So that's the one that you should consult. Don't make the mistake of reading the wrong table. There are two tables. One is in the English units, and the other one is in SI units. So if you're dealing in SI, go to the SI chart. This one is not the SI chart. This one is the US customary or the English units chart. So the second thing to note is that there are in the header, there are some values given already. So for example, the aluminum alloy 20146, the value of E will be 10.6 times 10 to the 3 KSI. This is not even PSI, this is 10.6, and this is the header 10.3. You have to multiply this value by this header, and that is still in KSI, not PSI. If you were to write PSI, it will be another 10 to the power 3. So a total of 10.6 times 10 to the 6 PSI. So you have to make sure you use this header also when you are dealing with this. In case of yield strength, it's directly given in KSI. There is no header, but it is still KSI, not PSI. So for example, the value of, you can see anything, steel alloys. For example, if you see the A36 steel alloy, very common steel alloy used, you can see its ultimate strength is 58 KSI. And its yield strength is 36 KSI. And its modulus of elasticity would be 29.0 times 10 to the 3 KSI. So you have to make sure you read the headers also and see what units are there, KSI or PSI. All right, everybody good? These are given in the back of your book. You can, I usually give you these in the exam also, these same tables, so that you can read the values from here. For your information, they are also given in the inside back cover. I'd like all of you to open your books, have a look at it, the inside back cover, and take a look at these two charts given there. One of them, of course, is the SI units one, and one of them is the British engineering system or the US customary system one. That one I'm showing you here. And the SI units one is also given there. All right, any questions, anybody? Mechanical properties. So these are the important points. There are two charts. One is in the US customary and the other is in SI units. You've got to consult the correct table. Then numbers in columns to be read with header in that column. This also I explained you. And use appropriate table for units required, means either SI units or the English units. Now, here I'm showing you, and this also I've taken from your book. This is a stress strain diagram for iron. And it's quite different to the one that I showed you. The one I showed you was mostly going on this side, but look at the iron one, it is going It doesn't have much of a, this is the fracture stress for this, 22 psi is the fracture, which is not much of a strength on this side, which is the tensile side. But if you see the, it is very good in compressive load. It goes up to about 120. So 5 times the value in compression. Its strength lies in compressive loads, not in tensile loads so much. For iron, we're talking of iron right now. So for iron, it's not very good in tensile loads. These are the tensile loads on the right hand side, and these are compressive loads. In compression, you know that the elongation is negative, or actually there is contraction. So this is negative contraction. You can see the negative numbers there. And this is the load, this is tensile load, this is the compressive load. Compressive load is shown as negative. So it has a much more. So you see, iron is always used in for example, RCC or reinforced concrete construction. Iron is used because the load there is always compressive. So that's why it supports. It has a lot of compressive strength rather than tensile strength. It's actually pretty brittle. It breaks off very soon. Any questions, anybody on this? All right, then the next thing I have is some more useful terms, and there's a nice graph given in the book which I'm going to show you now, in which you can see all these things. So something else I want to explain here is shown in this graph. So look what's happening. You start with zero stress, no strain. And as you increase stress, strain keeps increasing. And this is the straight line portion. We call this ratio, we defined as E. And E is given by stress over strain. So that is the ratio which we call modulus of elasticity. And usually the point where the proportional limit ends and the straight line relationship ends, that's called the elastic region. So up until here is called the elastic region. What happens in the elastic region? You load it, it keeps increasing. You start taking the load off, it will keep coming back. The strain will keep reducing till when you have zero stress, zero load, the strain will also become zero. This is called the elastic region, in which it doesn't change its it has no residual strain. This portion is called the elastic region. But a strange phenomenon is noticed that if you go beyond the elastic region, for example, you keep loading the material, it follows this path. Now you start offloading. Well, the strain starts to reduce. As you're reducing stress, strain also keeps reducing. But a point comes where it starts to follow. So the strain with the reduction in stress, the reduction in strain is much less now. And you see that instead of following back when you're reducing the load, it doesn't follow the same graph, rather it follows this graph. And you end up with a certain strain which is called a permanent set, because you loaded it so much that some of the strain is now permanently in the member. It never got back to zero. So this portion is called plastic region, and this strain is called the permanent set. I think this is shown in another graph also. It's not written here, but you'll see it. So please understand, if you go beyond the elastic region, up until here, if you stay within this elastic region, your load never exceeds this, then you're good. If you offload it, it'll come back to zero strain. But the moment you go beyond this, then you will never come back to zero strain. There will always be a permanent set there. So you come back now to this. When you offload, you don't follow the same graph beyond elastic region. Within elastic region, you come back on the same graph. Beyond elastic region, wherever you finish, if you want to come back, you might end up here somewhere, for example, if you start from here. So this is something you should understand. This is another useful term, permanent set. So this law is also called Hooke's law, the Young's modulus, which defines the Young's modulus. Another important term for you, Hooke's law. Then strain hardening or permanent set, I just explained to you. Strain hardening is when you get a permanent set. And that is what I just showed you. This is what I explained to you. The elastic recovery is not a full elastic recovery if you are in the plastic region. So these regions you should know: elastic region, plastic region, and permanent set, and strain hardening. These are the terms you should know. And more terms, more interesting terms are shown in the next graph, which I'm going to show you, which is also I've taken from the book, which is this. Now, please understand, this graph is not to scale. I think it is mentioned somewhere. Yeah, there it says. Conventional and true stress strain diagrams for ductile material like steel, which is not to scale. So don't think that sigma and epsilon vary exactly like this. These are not to scale. But this is just to show you all the different terms we have talked about. If you see, you start from zero stress, zero strain. You start loading, you follow a straight line up to proportional limit, PL. Beyond proportional limit, there is a yield point. And beyond yield point, without increasing any stress, the strain keeps increasing. This is where the material just yields. It yields for a certain time. This is what you see there. And this is the yield strength. This is also called the elastic limit, as I explained to you. Beyond this, there will always be a certain permanent stress. If you are below the yield strength, then you will come back to zero strain. If your stress is zero, then strain will also be zero. If you go beyond that, then there will always be some permanent strain. So you have to know these terms. For example, elastic region. What is elastic region? Elastic region is below the yield stress, because below that point you can come back to zero strain. Beyond that is plastic region. So elastic region, plastic region, yielding, I explained to you that yielding occurs once you reach the yield stress. Beyond that, without increasing any stress, the material just yields. And after that, then there is what we call the ultimate stress. That's the maximum value that it can take, ultimate stress. And beyond that is the fracture stress. And fracture stress is less than the ultimate stress. This is the question I've asked you. I'd like you to investigate on your own. How come the fracture stress is less than the ultimate stress? Any questions, anybody? Another term you can see there is called, well, these two terms, strain hardening. This is the portion where there will always be a permanent stress. This portion is called strain hardening because if you reach this region, even though you reduce the stress to zero, the strain will not be zero. There will be a permanent set. And beyond that, there is a portion which is called necking. And necking happens, and this is something which I normally would have done in a physical class, in a person-to-person class. I do arrange a demonstration in our lab where we go and see this, when the class goes and see testing, material testing of some material, and you see the tensile testing machine, and we give you a demonstration of how the material necks. Necking means, and let me show this to you, that so let's say this is your specimen that you fix between the two heads of the machine, and then you apply a load. So this, now you put your specimen in normal stress, and as you increase the stress there will be strain. It will start to increase in length, and when it increases in length, what happens to the diameter? Well, the diameter will reduce. So as the length increases, you will find it becomes something like, oh, no, not that much. So can't be more than how it started. So something like this. This is called necking. That means its diameter starts to reduce in the center, and it keeps reducing till ultimately it breaks. So this is maybe I have a picture. You have a picture in the book also. You can have a look at the material testing specimen. It looks something like this. And the specimen I showed you had, so it had, for example, this is the original material. It has threads there on this end and threads on this end. And then there are two marks there which sets the original length. And then when you load it to a certain value, for example, you load it to a certain value, and the load is known to you, and now you see the length, the marks have gone that big. So the length has increased. It was originally this much, which is about what? This much. So this is the delta L you see. This is the original length, L. So this is the original specimen with the mark points. And we said it could be, for example, 2 inches. And there then, when you apply the load by the machine, it extends and the diameter reduces. This is called necking. The reduction in diameter is called necking. And it ultimately fails. Correct. That's the answer, yeah. Can you explain it a little more to the class then? Yeah. So what happens is that the area at the, so I'm explaining now why the fracture stress is less than the ultimate stress is, because now the area has also reduced quite a bit, you see. And that area reduction, because area is in the denominator, so it causes the fracture stress to be less than the ultimate stress. All right. These were the important terms, and I'd like you, when I ask you to draw a diagram of a ductile material, I'd like you to show all these points. So elastic region, plastic region, proportional limit, yield stress, ultimate stress, fracture stress. Those are the things. And if you take into account, well, really speaking, if you see this line, this is the one which is taking into account the area reduction and fracture stress. If you If you took into account the reduction in area also, then true fracture stress will be much higher than the ultimate stress. You see what I'm saying? And this is what just somebody pointed out, that this is the answer to that question, that in reality, the true fracture stress is much higher. But if you don't take into consideration the area reduction, then of course the fracture stress is below the ultimate stress. Any questions, anybody? I guess we are ready now to look at some problems. There's something on numbering system. So there are two numbering systems. One is the AISI, American Iron and Steel Institute. And then there is the Society of Automotive Engineers. They both have their own systems, and they depend upon the carbon percentage in the material, in the alloy, steel alloy. For example, carbon steel. So you take wrought iron and then you start increasing carbon percentage. Based on that, the properties vary. So soft steel has 0.1% carbon, structural steel has 0.2% carbon, machine steel is 0.6 carbon, which is considered pretty hard steel. Machine steel is pretty hard steel. And then if you heat treat it further with 0.6% carbon, this is called hard steel, and 1% carbon is really spring steel. So these are the different kind of, depending on the carbon percentage in the wrought iron, you can change the properties, and this is how they are called. Another way of classifying these is also, I think, low carbon steels, which have a carbon percentage of 0.05 to 0.25%, then medium carbon steels 0.26 to 0.54, high carbon steel 0.55 to 0.95, and then very high carbon steel 0.96 to 2.1. Now, as the carbon content increases, it keeps becoming more and more hard, but at the same time, it keeps becoming more and more brittle. So the lower the carbon content, the more is the ductility, the more ductile it is. But as you increase carbon content, it keeps becoming harder, but as well as more and more brittle. Then there is a whole numbering system, and for example, we've been using steel alloy 304. So what does that 304 mean? Or aluminum alloy 2014 or 2016. So what do those numbers mean? There is a method of identifying what is the meaning of that numbers. And I have a thing in the end, I'll show you. You can go through it in your own time. That explains you how the numbers are given. Now we can now start doing some problems. Here is the first problem. Determine approximate modulus of elasticity, and you're given the stress strain diagrams for these. Now this one is the original diagram with not an expanded scale, and this is the same material, same diagram, but with an expanded scale. So you can see this is 0.2% and this is 2%. So this much of the graph up to 0.2% would be somewhere here. This much of the graph is shown here. This whole thing in this graph is only up to about this point there, somewhere there. So to find E, the best way is E is defined as the sigma over epsilon. So you go in this portion of the graph and find E. what I would do is I would try to pick a point where it is actually both the lines are crossing. So if you look at this point, then you can read off this is also a line there, and then there is a line here also. You can take any other point also, but for example, if you take this point, you can read this value as 50, but then you will have to approximate this value. It's not on the line, but if you, the advantage of this point is that you can read off this value as well as this value. So for this much stress, what is the strain? This is the strain. I'd like you to try and read it off. For me, I would like to, maybe I would read it as if this is 50, this would be about 60, 60, 70, 80, 90, 100. So this is 60, excuse me. Sigma value at this point is 60 megapascals. So let's write those. Excuse me. Problem 1. Man wants you to find E. E is given by sigma over epsilon. From the graph, we can notice what is sigma at that point that I showed you, which is, if you're looking at this point, it is 60 megapascals, correct? And what is the value of epsilon?
0.0006.
Let's see, this is the line we are looking at. So this is 246, yeah, 0.006.
One more zero.
One more zero, 0006, you're right. So the strain value is 0.0006, and it doesn't have any units, but we can still write millimeters per millimeters. So what will be E then? E will be sigma over epsilon, so 60 divided by 60 megapascals, which is 10 raised to power 6 pascals, divided by 0.0006. And this will come out to what? So
I have 1 times 10 to the 11.
10 to the 11, which means 100 gigapascals. That's the value of E you get there. Everybody good? The next part is B, find the yield strength. So this was part A, find E. And part B is asking you to find the yield strength. How do you find the yield strength? Well, you go to the graph and you go to 0.2%, which is this point, 0.2%, and there you plot a line parallel to this line. And when you do that, you'll probably end up on the same line. So this is the value you got to read off. How much is that? If this is 50, this would be 70 megapascals. Everybody good? So in the exam, you will have to draw this line for me. I'm not drawing it here. I can draw it on the board, but this is the kind of line you will have to be showing me. 0.002. At this point, 2.2%, you draw a line parallel to this line, the original one, this one. Exactly parallel to this, and wherever it cuts the graph, that's the value you read off. And in this case, it comes out to, so my sigma yield strength comes out to 70 megapascals. Part C is ultimate strength. So for ultimate strength, you got to go to the graph on the right, and I'd like somebody to read it and give me a value. What is the value of ultimate strength?
245.
Approximately 245. And what are the units?
Megapascals.
Megapascals. And the last thing he's asking you to do is tell them, say the material type. What is the material type depending on these properties? So we have to look for a material whose E is 100 gigapascals, whose yield strength is about 70 megapascals, ultimate strength is about 245 megapascals. So we go back to the back of the book. I'd like you to open your books. On the back of which table are we going to look at? So not the first one because that deals with customary units. We will use the SI units one. Yeah, the second one. So there, if you go in the, if you look at the column for modulus of elasticity E, and you look for one which has approximately 100 gigapascals. So you find that there is none with exactly 100, but there is one, the closest one is 101. And what is that? For this E equal to 101, you also check the yield strength, it is 70. So these are the two things that will confirm. And the last one is that the ultimate strength is 245 we found. And for this particular copper alloy, it is the closest. We have E as 101, we have yield stress as 70, and ultimate strength given here is 241. Our graph is approximate and we still read close to that 245. So from this table, then we can say that this material for which we are seeing the graphs are given in this problem, it is really the red brass copper alloy. So I will say material type is, I can write it here, material from table is copper alloy, red brass. Is it red brass? Yeah, red brass. And the number is also given there.
On the test on Friday, will we be receiving like a formula sheet or anything regarding that table that you were looking at?
Yeah, you will be receiving. So the formula sheet I have for this exam, it has these, both these pages also included, which are in the back of the book.
Okay.
So both these tables are there in that.
Okay, awesome. Thank you.
Welcome. Any other questions? We can move on to the next problem then, which is there. Please read the problem. The problem says, suppose test conditions and result on a tensile test specimen are as follows. And this is the same kind of situation as I showed you on the universal testing machine. You have a specimen whose initial length between the two dots is 2 inches. Its cross-sectional area is 0.1 inch square. And then he's giving you the loads. When he put the load of 625 pounds on it, the change in length was so much. For 1250, that means you doubled the load. That delta L was so much. You again doubled it. Delta L was also doubled. So it seems these three readings are in the straight line portion. And so on. And then he says that the maximum load it could take was 7,500 pounds, 7,500 pounds. Now, he's asking you to determine the modulus of elasticity, or Young's modulus. How do you find that? You start with the same thing. You say that Modulus of elasticity E is defined as sigma over epsilon. So we need to find sigma and we need to find epsilon. What is sigma? Sigma is given by the load over the area. And you can take any one of the loads because in the straight line portion, you can see as you are doubling the load, the delta L also doubles up. So this is the straight line portion. Let's say we take the 625 pound load. Then what I can say is that sigma will be 625 pounds divided by the area. And what is the area? He's given you the cross-sectional area is already given 0.1 inch square. So it becomes 6250 psi. That's the sigma. And what's epsilon? So epsilon we need to find now. Epsilon is defined as delta L over L. In this case, when we loaded it to 625 pound, what was delta L? The value is given there, 4.46425 times 10 to the minus 4 inches. And this is divided by the original length, which is 2 inches. And so epsilon ultimately comes out to, if you do the math there, epsilon came out to 2.232 times 10 to the minus 4 inch per inch. So therefore E is equal to sigma over epsilon 6250 psi divided by 2.232 times 10 minus 4, and this comes out to 2.8 times 10 to the 7 psi. You can leave the answer like that, or it is better to write it in KSI because our tables are also in KSI. So this will be 28 times 10 to the 6, which is times 10 to the 3 KSI. Hang on, how much does it come out? Let me check this number for a minute. This is 2. So I got 6250 divided by this. So this comes out 2.8, which means this 3 and 4, 7 there. So 2.8 times 10 to the power 7 psi, and which means 28 times 10 to the power 3 ksi. Yeah. All right. The next thing he wants you to find is determine the modulus of elasticity, ultimate strength. So how do you find the ultimate strength? Maximum load is given. So sigma U will be the maximum load, P over A again, which is the maximum load is 7,500 pounds divided by the same area, 0.1 inch square. This is 75,000 psi. And lastly, he wants you to find the material type again. So you go back to you go to the back of the book again, and this time you're going to look in the US customary thing, and you look for something with an E value of 28. Do you find one? Yeah, it is the stainless 304 alloy. If you look at the book on the table, you will find that E is equal to 28 is for actually only one of them, which is the 304 stainless steel alloy. And for that, you will also see that the ultimate strength is given as 75 KSI. This is what we found. So the answer is material type would be from the table is stainless steel 304. All right, everybody good? Any questions? I can move on to the next problem then, which is this. These are simple problems really, nothing much there. And please read the problem. And the man is now saying that suppose a beam with a circular cross section has the following properties. Initial length 2 meters. Cross sectional diameter 0.01 meters. Modulus of elasticity is given as E value of 120 GPa, gigapascals. And then yield strength given as 924 megapascals and ultimate strength given as 1000 megapascal. The man wants you to determine A, elongation when loaded to half the yield strength. So let's see what is given. E is given as 120 gigapascal. And yield strength, sigma yield is given as 924 megapascals. What else is given? Ultimate strength given there. So he wants you to determine elongation. That's the first thing he's asking you to find. Elongation is usually given by delta L. So this is what we want to find. And we know that E is given by sigma over epsilon. And to find delta L, we need to find epsilon, because epsilon is delta L over L. L is given, initial length. If we find epsilon, we can find delta L. And to find epsilon, what can we say? From here, epsilon is equal to sigma over E. E is given, and sigma we have to find. What is the sigma for this? So he's asking you to find elongation when loaded to half the yield strength. So yield strength is 924, and he's saying if sigma is half of that, so in this case, therefore, sigma is 924 times 10 to the 6 divided by 2, and all divided by E. E is given as 120 gigapascal. And if you solve this, you find your your epsilon comes out to epsilon came out to 0.00385, and therefore epsilon is equal to delta L over L is equal to 0.00385, which means delta L is equal to this quantity multiplied by the original length, which was 2 meters. And so this came out to 7.7 times 10 to the minus 3 meters, which is approximately equal to 7.7 millimeters. The next thing he wants you to find is load for yield strength. So simple. Part B, we want to find the load for yield strength. So yield strength is sigma yield is the load for yield strength divided by the area. So this is what we want to find. It will be area multiplied by the yield strength, which is 924 times 10 to the power 6 is the yield strength multiplied by the area, which is pi 0.01 square over 4. And this comes out to 72.6 kilonewtons. And lastly, the man wants you to find the maximum load. Maximum load we can find from ultimate strength. So sigma ultimate is P max divided by A, therefore P max is equal to sigma U multiplied by the area. You put the numbers and you find the answer comes out to, let me put the numbers also, 1000 megapascals multiplied by the area, pi into 0.01 square divided by 4, and this comes out to 78.5 kilonewton. I have another example problem for you to be doing in your own time. And this is a book, this is a question from the book. You can, I think this is the one, group problem solving, in which he has shown a strut supported by a pin at C and an A36 guy wire AB. So that's the wire AB. And if the wire has a diameter of 0.2 inches, determine how much it stretches when the distributed load acts on the strut. So you want to find the delta L in this AB. You can try it at home and find the solution. Answer is given in the book. And that is all we needed to talk about today. Tomorrow we'll conclude this chapter. And maybe I can give you, well, the answer is given in the book, basically. I can also give it to you. It is for this last problem that I showed you from the book. The answer you will find is the change in length in AB will be, delta AB came out to 0.0821, 0.0821 inches. That's the answer.
Professor, is that a grappa question or where's that at located?
Sorry?
Is that an example question? Or where's that located?
Oh, I have to look in the book.
Is it a problem or?
It's a problem. It's one of the problems.
Okay, that's it.
So I'm sorry, I never noticed. I think we've gone
That's okay.
several minutes over the time. Oh my God. Time flies, man. I thought this was a small lecture, so I won't go over this. I'm leaving you to watch this little video. This explains you the numbering system. And then this is your homework for tonight. Thanks, guys. Again, I'm sorry I took, my time ended at what, 10:50, and I have overspent 17 minutes. I don't believe it. Sorry, guys, once again. But thanks for staying with me. I'll see you tomorrow then.
Dr. Baza,
Mhm.
are you going to be uploading this PowerPoint later? Because I don't see it on the Blackboard right now.
Okay, I'll upload it. Thanks for reminding.
Okay, thank you.
All right, bye-bye.